Hello, this is Mr. Bryce, and just like to do a couple examples of hypothesis testing, specifically around a sample or a population mean, because that's what we were seeing this week. So remember, the whole point of this is we're going to get a p level and we're going to compare it to alpha. And if our p level is less than alpha, we're going to reject the null hypothesis. If our p level is not less than alpha, we're not going to reject the null hypothesis. So remember, those are the two things that are going to happen. You either reject H0 or don't reject H0. So here, a researcher thinks that firstborn children have higher cholesterol levels than other children. So we know that the mean cholesterol level for all children is 190 with a standard deviation of 15. So this researcher surveys 100 firstborn children at random and finds that their mean cholesterol level is 192.5. So the sample mean is higher than what the population mean would be, so it does kind of suggest, well, maybe it is. Maybe firstborn children do have higher cholesterol levels. But what this hypothesis test lets us do is actually test this mathematically. So the parameter we're looking at here is the population mean, right? Or in other words, mu, which is that little cursive lowercase m thing. So our hypothesis, our null hypothesis and alternative hypothesis have to do with what the population mean is for these firstborn children. So our null hypothesis is that there is no difference, that the firstborn children have the same mean cholesterol level as any other children. So our null hypothesis is that the mean is 190, because then it would be the same as all other children. We're testing the hypothesis that they actually have a higher cholesterol level. So we're testing to see if the population mean for firstborn children is greater than that. So to do this, there's several different ways to do this. You can do this with confidence intervals. You can do it with finding probabilities with areas. But the way I like to do it is in stat tests and then ZTest. So use ZTest, and then we got to fill in all this stuff here. And if you take a look at the post I put on D2L, it tells you what all this stuff should be. This mu naught is the population mean, which here is 190. And then sigma is the population standard deviation, remember, so the population standard deviation is 15. X bar is our sample standard deviation. These are all the same letters we've been using all semester. So the sample mean, sorry, is 192.5. So in our sample, we got 192.5. And then n is the size of our sample, which is 100. And we're looking for evidence that mu is actually greater than 190. Right? So we pick that one because that's where our alternative hypothesis is. So you can either calculate or draw. I like to draw because it draws you a nice picture of it. So here's the distribution of the sample mean. Remember, we know the sample, we know the mean of that and the standard deviation of that from a couple weeks ago. And the probability of getting a sample like this at random is 0.047. Right? So our p level is 0.047, which is less than alpha. Right? So our p level is less than alpha. And what does that mean we're going to do? That means we are going to reject our null hypothesis. So if we reject this, that means that it suggests that this is true. So our conclusion is there is sufficient evidence to suggest that firstborn children have higher cholesterol levels than other children. All right, and this is just the interpretation of this result here. All right, so this is how these work. They'll always tell you all of this stuff here, and then you can just plug it into here, and it'll give you the P level. Let's see another example of this, which is a sociologist is interested in the body fat percentage of college students. So she thinks that college seniors have different percentages of body fat than freshmen. Now, she's not sure whether they're going to be higher weight, so maybe they stopped exercising, ate less healthy food, or maybe they lost weight, maybe they have stress issues and stuff like that. So she's not sure if it's going to go up or down. She just thinks it might be different. And we already know that the percentage of body fat for college freshmen is 25.4% mean, with a population standard deviation of 8.5%. So she samples 131 college seniors at random, finds their mean body fat's 30.1%, and is that sufficient evidence to conclude at the alpha equals 0.10 level that the percentage body fat of college seniors has changed? So this time again, we're looking at the population mean, mu, which here is going to be the body fat percentage. H naught is the statement that there is no change, that college seniors weigh the same as college freshmen. So the null hypothesis is that mu is 25.4 for seniors, just like it was for freshmen. And H1 is that it's changed. Now, we don't know if it's bigger or smaller, but I'll just write not equal to, because I don't have a key for that. But it's the equal sign with a line through it. So these are our two hypotheses here. And remember that H naught is always going to have an equal sign in it, and H1 is not going to have an equal sign. So, all right, so we need to find the P level for this. And that, again, is back in stat tests. And you can hit up ZTest right here. This time, our mu is 25.4. Our standard deviation in here is 8.5. You could also write all these as decimals too, and percent of percents. You get the same thing. Sample mean was 30.1, and the size of our sample was 131. And we are 131. What we're testing is that our population mean for seniors is different than our population mean for freshmen. So we're testing for inequality here. And we can draw, remember this is called a two-tailed test here. We can draw this. And is this what I wanted to do? 25.4. I didn't think it was that when I did it before. So let's double check. I put in this stuff right here. So Z-test, 25.4, 30.1, and yeah. So, all right. So our P level is very, very, very small for this. In fact, it's so small that just said it was 0. And if I calculate it, it might be, yeah, this probability is very, very, very small. It's 2 times 10 to e to the 2 times 10 to the negative 10. So it's 0.9 zeros and then a 2. So our P level is very small. It's 0.123456789 Well, what's our result? Well, that is definitely less than alpha. So our conclusion then is that since P is less than alpha, we're going to reject H naught. And then our conclusion is that there is sufficient evidence to believe that the weight of college seniors differs from the weight of college freshmen. Now, just as a change here, what if instead of 30.1%, we had, say, 24.9%? So what if in our sample of 131, the mean body fat percentage was, let's say, 24.9%? How would that change this if instead of 30.1% we had 24.9%? Well, it's the same thing we're doing here. Test, Z-test. The only thing that's going to change this time is our sample mean. All right, so now it's 24.9%. All right, sample size is still the same. We're still checking for inequality. And we can draw this. All right, so here's a picture of it. And this time our P is 0.50. All right, so now our P is 0.50. So the result this time is P is greater than alpha. Right? So we're going to not reject H0. And the conclusion from that, then, would be that there is not enough evidence to show that the body fat percentage of college seniors is different from that of freshmen. All right, so we're getting our P level here, which is the probability of getting a sample like the one we got. And if that sample is unusual, normally unusual, remember, means less than 5%. So that's usually what alpha is. But you can have here it was 10%. Then our sample is unusual enough to suggest that maybe there actually is a change. So hopefully this gave you a couple of good examples for this. There's a ton more online. There's a ton more in the book. There are, like I said, multiple ways to do this. So if you go find other resources on YouTube, other sources online, they might do these with confidence intervals or with by just drawing a picture of it and finding the probability of getting a sample like the one you did. But it's the same idea, where you're basically figuring out, is our sample weird enough to suggest that something has changed?